In the previous video, we left off talking about the Bohr model of the atom and how it had some limitations. Remember that in the Bohr model, the place where the electron is found around the nucleus is called an orbit, and they are circular in nature. They only differ in the size of the circle. The farthest away from the nucleus, the larger they get. However, this fails to explain the line spectra of more complex atoms. Therefore, an updated version or a slightly different model needed to be described, and so the quantum mechanical model was the one that replaced the Bohr model. In this model, we do not specify the location of an electron, but instead it defines a region of space where the electron may be found. And that particular region of space, three-dimensionally, is called an orbital. It differs obviously from orbit, and we now have orbitals. This is the area of space where the electrons are most likely to be found. And unlike the Bohr's model, they were all circular and varied in size. Quantum mechanical orbitals vary in shape as well, and we're going to see how they do that. First, let's kind of try to figure out what an orbital is. This is really just a region in three-dimensional space where an electron is most likely to be found. Let's look at an example. Your book mentions a sparkler, so let's kind of talk about this because we're all familiar with it. So if I light a sparkler, it's brightest right at the tip, right? And if I liken that to where the nucleus is found, then if I draw a circle about 5 centimeters from the center, the nucleus, and then draw a sphere around it, so all around three-dimensionally, I will find that 90% of the sparklers are contained within that sphere. Yes, I have maybe some that will fall outside of that sphere, but 90% of the sparklers are within this sphere that is 5 centimeters in radius. Now, unlike the sparkler, we cannot know exactly the coordinates of an electron, and we cannot really map them that they're here exactly or it is here exactly. Instead, we use quantum mechanics, which we're not really going to go too deeply into for this class, but quantum mechanically we can calculate the probability of finding an electron around the nucleus. It's a probability density map of a location of an electron. This probability map is called an orbital, an atomic orbital. So it is an area of space around the nucleus where the electron is most likely to be found. Now this shape can be circular, like the example with the sparkler, or it can have different shapes, and we're going to look at them in a little bit here. The important point that I want you to remember is that these atomic orbitals that we're going to talk about are really just calculated areas of space where we have the highest probability of finding an electron. Now, for the atomic orbitals in the quantum mechanical model, we have certain divisions. In the Bohr model, we only had the quantum number, the principal quantum numbers, so shell number 1, number 2, number 3, etc. Well, in the quantum mechanical model, those main shells are subdivided into a subshell and orbitals. Let's take a look at how we determine those. The principal energy level is once again denoted by a whole integer. N equals 1, 2, 3, 4, 5, etc. So a whole number. Now in this model, the energy levels, or shells as they are called, can be subdivided into sublevels. Those energy sublevels or subshells are denoted with letters S, P, D, and F. Each of these sublevels can contain, in addition, one or more orbitals, atomic orbitals. Note that these are only areas of space where we have high probability of finding an electron. Nothing more. The number, so if you note, the number of energy sublevels and the number of orbitals, they depend on the principal shell number, 1, 2, 3, 4, 5, etc., that's an integer. So let's look at this table here that gives us sort of an overview of shells, subshells, and orbitals. So if n equals 1, that's the simplest first energy level, then that energy level can only have one sublevel designated, and the simplest of them is S. The number of orbitals in that first energy sublevel is only 1. So for n equals 1, we can only have one S, and no, so the sublevel and the orbitals are the same. If I have n equals 2, so now I've moved on further out from the nucleus in space. N equals 2 can have two sublevels, the S and the P. Note that for n equals 1, I only had the S, but for n equals 2, I have the S and the P. The number of orbitals in the sublevel S is still 1, just like it was for n equals 1. But for the P sublevel, I have 3 orbitals. For n equals 3, I have 3 sublevels, the S, the P, and the D. And S has 1 orbital, the P sublevel has 3, and the D has 5. For n equals 4, I have 4 sublevels, S, P, D, and F. And the S has 1 orbital, the P has 3, the D has 5, and F has 7. Note that the number of sublevels corresponds to the principal quantum number n. So for when n equals 2, I have 2 sublevels. When n equals 3, I have 3 sublevels. When n equals 4, I have 4 sublevels, and so on and so forth. Note also that the number of orbitals is always odd. So it starts with 1, 3, 5, and 7. S will always be 1 orbital, P will always be 3, D will always have 5, and F will always have 7. Now let's kind of look at pictorially, just to give you more of a visual idea of what these shells and subshells and orbitals stand for. So if I'm, this is the example in your book, but if I'm in a shoe shop, and I have different cabinets where I'm storing shoes. If this is my simplest cabinet, this is n equals 1. This is my first shell. I also have 1 subshell and only 1 place to put a pair of shoes. So 1 orbital. This is the simplest. If I go to n equals 2, so this is my second cabinet on top of the first one. So if I took this and I put it right here on top of the first cabinet, the cabinet stands for my shell. This is cabinet number 2 or shell number 2. But now I have 2 little shelves within that cabinet. This is my first shelf, my first subshell. It's designated 2s because it's my second cabinet, but it's still s because I can only fit just one orbital in here. That's the orbital. It's still 2s. Now, when I go in the second shelf, the second subshell, which is p, I can fit more shoe boxes, more orbitals. And so I have 3 shoe boxes that fit in here for the p shelf. If now I move to the third cabinet, I have three shelves now. I still have the S and the P, just like I do with the second cabinet and the first cabinet, but now I'm adding a third shelf in that cabinet, and that shelf contains 5 orbitals, 1, 2, 3, 4, 5. The same thing with the fourth cabinet. Note that these get larger and larger, and they move away from the nucleus. And the larger they are, the higher the principal number. From 1 to 4, you can see that I have more subshelves, more shelves, and within those shelves, now I can fit more orbitals, more pairs of shoes. For the 4f subshell, I can fit 7 orbitals, 1, 2, 3, 4, 5, 6, 7. This sort of gives you a visual idea of what the divisions might look like. In the Bohr's model, we only had circles. We didn't have these subshell divisions and orbitals at all. We just had 1, 2, 3, and 4. So it was much simpler than the quantum mechanical model. But as we said earlier, because atoms increase in number of electrons, they don't just have one electron. The model has to become a little more complex to be able to describe those additional electrons as well. Now note that this isn't a perfect model either, and the math gets very complex very quickly, and so these are more approximations than anything else, but needless to say, this model is more complex than the Bohr model and is the current one that we use in chemistry and physics. Now let's talk about the orbitals themselves. So the s orbital, or the first shelf, if you will, is spherical in nature, just like that sparkler. The probability of finding the electron, or the electron density, is highest in the center towards where the nucleus is found. And then as we move away from the nucleus, the electron density, or the probability where the electron might be found, decreases. So here you go, you have a higher probability, as the color suggests. It's a deeper blue here, which means that we can find the electron. Most likely we will find it here compared to the outer edge. So the s orbital has a spherical shape. Now if we move to the before I get there, but the s orbitals from the first energy level, the second, the third, and the fourth, they're really spheres. They're the same, they look the same. The only difference is that they increase in size. So you can see for n equals 4, the s sublevel is much larger than for n equals 1 sublevel. So they look very much alike. They're spheres, just those radii get larger and larger as I move away from the nucleus, obviously. When I'm looking at the p orbitals, now the shape changes a little bit. So in the second energy level, where n equals 2, I don't just have the s sublevel, right? Not that this is the first shelf. I also had the second shelf that I added, and I could put 3 pairs of shoes in there. So these are 3, they look like dumbbells, and they are oriented differently in space. So they're perpendicular to each other, but one is along the x-axis, one is along the y, and the other along the z-axis here. They lie perpendicular to one another. And the nucleus is right at the intersection of those three coordinates, so right in the middle here. Now you can see that this is the p orbitals have a much different shape than the s orbitals. And as I move on to the third energy level and the fourth energy level, I now add the d sublevel and the f orbitals. And you can see that the shapes are all different. Note that you do not have to memorize what the shapes look like, but you do have to know that the third energy level contains three sublevels, the S, the P, and the D. I haven't shown the S and the P here, just the D, because I wanted to show you the shapes of the d orbitals. The S and the P orbitals for the third energy level looked just like the s and the p orbitals for the second energy level. They're just larger because they're now further away from the nucleus. The f orbitals are highly complex, and I haven't included them here, but for energy level n equals 4, you will have s, p, d, and f as well, f orbitals, and there are 7 of those for the f orbitals. Note that as I go from the S to the P to the D to the F sublevels, just like if I go from energy level 1, 2, 3, 4, the energy increases. So if I have, let me go back here, if I have an electron in the energy level 2, and I have that electron in the s orbital, and I have another electron in the p orbital, one of them, it doesn't matter, even though they're in the same energy level, n equals 2, the p orbital is slightly higher in energy than the s orbital. And that electron then has a little more energy than the first electron that is in the sub-level S. The same thing if I move to the d orbitals of the third level, that has a higher energy than the p and the s, and so forth. I wanted to show you, leave you with this image here. This is sort of a combination of the first and the second energy levels, so n equals 1 and n equals 2, just to give you an idea what they look like three-dimensionally. In the center here is my nucleus. In this grayish blue circle or sphere, this is my first energy level. It's n equals 1, and n equals 1 only has one subshell, the s subshell, and one orbital. So I have only one orbital here, the 1s subshell. When I move to the second energy level, note that I have the 2s subshell and the 2p subshells. And you can see this sphere now is larger, but it looks very similar to the 1s. But this is larger, and this is the 2s subshell. And then in addition to that, I have the p orbitals around the nucleus as well. And you can then imagine that the third subshell, the 3s, first of all, is going to be a sphere around, a bigger sphere, but larger than the 2p orbitals. And then the 3p orbitals are going to come outside of that 3s orbital, and so on and so forth. So you're going to see how, at least I want you to kind of see how they can overlap just a little bit in three-dimensional space, but they're around each other. And these are all areas where I could have an electron here, an electron here, an electron here, depending on how many electrons the atom has that can be populating these orbitals. We will get to how we do that, how we distribute electrons in the next video.